All right. Hello, everyone. Welcome to CIS256. Today, we're talking about a special type of problem, which is called optimization problems. In particular, we'll touch base on some of the common algorithms in those kind of problems. Especially, we use Knapsack problem as an example to talk about greedy and dynamic programming methods. So what is a optimization problem? Basically, in our as far as our subjects is concerned, we're talking about a objective function that is to be maximized or minimized, right? For example, if you want to minimize the traveling time from A to B, or you have a set of constraints, typically must be observed. For example, you have a constraint of, you have a budget of $100, or you have to arrive in destination before 5 p.m., for example, right? So a set of, or a objective function or functions that is to be maximized, minimized. That's optimization problem. So in particular, in real life, many problems of real importance can be formalized as optimization problem. And a lot of those kind of problems are, computationally challenging. So we use some of the approximations or algorithms to take a practical approach, find a pretty good approximation to optimizing problem. Might not necessary to be the optimal solution, right? So there is a trade-off between a accuracy and speed and so on. So, all right. So let's talk about one type of problem, right? So optimization problem is knapsack problem. So what is knapsack problem? Knapsack is also known as a backpack in American. So you have a backpack that can take some items, but you have a maximum weight, for example, allowed. And you have a couple of items with values and weight. So this type of problem, right? So the constraint is going to be the top weight, like 15 kilograms in the backpack. So how are you going to, decide which items to take in the backpack so that you can optimize the value, you can maximize the value in this case, right? And provided you cannot take more stuff than you can carry. And also in knapsack problem, there's two variants. One is 0, 1, means you either take the item or not. One is continuous fractional knapsack, which you can actually divide the item into a smaller fraction. But in this problem, we're looking at the 0, 1 knapsack problem. Okay, so 0, 1 knapsack problem. Each item, we can represent it as a pair, a tuple in Python of value and weight, okay? And then the constraint is the weight, total weight is no more than W. And in this model, we use a vector L or list in Python of length n to represent a set of available items. Each element of the vector is an item of a pair of value and weight, remember? And then we have a vector v of length, same length, to indicate whether or not you're taking an item. So you have n items. Each position in that list represents that item number, and the value of that number is either 0 or 1, means if you take it or not take it. All right. So in other words, let's do this more formally. A knapsack 0, 1 knapsack problem is basically an objective function that maximizes the value. So there is a sigma means the summation, right? Summation from 0 to n minus 1 means you summation all the items in the list, where you take the value of that item, multiply. The v of I is basically your, a vector. Remember that if you are taking that item or not. So if you take it, it's 1, otherwise 0, and multiply by the item's value to maximize it. So you can choose different v of I and get a different set of values. Okay, and subject to the constraint that the summation of all the items weight times the same vector is less or equal to W. So that's the formal definition of 0, 1 knapsack problem. All right. So if we naively think about how to maximize or minimize, optimize this problem, what we can do is, if for limited items, we can enumerate all the possible combinations of items. Like, for example, we have 3 items, you can just pick the first one, not to pick the first one, pick the second one, not to pick the second one, pick the third one, not to pick the third one. Each position, you have 2 decisions to make, either pick it or not pick it. And each decision will result in a different combination, right? And if we generate all the subsets of the items, we call this a super power set. The power set is basically from all the subset of combination of items, okay? And how many set is there if for n items? Each one you can take or not to take. Well, that's gonna be 2 for each position times 2 times 2 times 2. It's basically 2 to the power of n. N is the number of items, okay? So you can see when n get bigger, this power set, number of power sets grow very quickly, exponentially. Of course, while you're doing this power set, you can remove early if the combinations, the total weight like this is greater than W. In other words, every time you have a combination, you use that to calculate the value. You first look at the weight. If it's greater than W, you don't even pick that, right? You remove all the combinations whose total value exceeds the allowed weight. And from the remaining combinations, you can choose anyone whose value is largest. So basically, you take the maximum out of remaining combinations. That's a brute force algorithm. So, like I said, how big is the power set, right? So recall that for that vector, you have you either take or not to take. So the number of binary numbers can be represented as 2 to the power of n. Basically, it's a binary number, right? Of n digit binary number, and the total of different numbers is 2 to the power of n. If there are 100 items to choose from, the power set is of size this number, which is astronomical, or 2 to the power of 100. So that's not practical, right? It's very big numbers. Are we just being stupid? No, 0, 1 factor is inherently exponential. There's a better solution, okay? So let's take a look at the greedy algorithm now. So greedy algorithm, basically the algorithm is like that, right? If the knapsack is not full, if you can still take in some items, you put which item to pick, you put the best available item in the knapsack. So you have a list of items, you sort it in the, in the order that's deemed to be best value. And every time you just pick the best one for the next item, and until the knapsack is full, right? So what's the best mean? That's actually arguable, right? You can take the most valuable or least expensive, okay, least weight, or highest value to unit, which is a density. So these are all candidates for the best definition, best function. Let's examine one by one. Here's the example. You go to McDonald's, you order some meals, okay? And in the manual, they give you different calories and values of food, but you have some preference, right? You like donuts more than apples, okay? And you have a budget. Your total weight is for example, your maximum meal budget for calories 800. How to choose to eat? Now it's a knapsack problem, isn't it? So here you go. Here is a list of menus with food, value, and calories. The wine, beer, pizza, burger, fries, Coke, apple, and donut. And each one has value and calories. So you want to pick, the best value to calorie ratio, or maybe just value or inverse of calories. Okay, so how to do that in code? Now here is a class that describes the food menu, food items that you're gonna order, and we just capture the name, value, and calories. Okay, now let's build the menu of foods, which is simple. You take the names, list of food names, and list of value, list of calories, and then you build this class object one by one. So in this case, we append the name, value, calorie, triplet to the food and return the menu. Okay, so let's implement a greedy algorithm, which takes items. Remember, the items is the list of foods, right? And you have a constraint maximum cost, which is the calories. And then the third item is called a function. This is a function name that used to compare stuff, right? So remember, in Python sorted function, you can have three parameters. You have a list to be sorted. You have a key to be sorted. It's a key function. And you can determine if you want to reverse that function, reverse that key. Right? Sort by ascending order or descending order. In this case, we want to sort by descending order. Right? So the maximum values was put to the first. Now, how to determine the maximum is a comparison function, which is called key function. Okay, so first of all, your total value cost is initialized to 0. And then I'm looking at all the items in the list, copy. We make a copy, right? And the copy is already sorted, remember? So, and because it's a greedy algorithm, we just pick the first one in the list, which is the guaranteed to be a maximum value. So we add the cost of the first item in that list and adds the cost, and we compare it to the maximum cost right away. If that's above the maximum cost, we don't need to pick it, right? We just go to the next one. So every time we guarantee to pick the best value, next by next. But this line is basically to guarantee that you're not exceeding the maximum cost. That's constraint. And then if that constraint is satisfied, you append this to the list, the result. And don't forget, you have to update the total cost, which is that item's cost function, and total value is item's value. So now you just go through everything in that list until you are not able to take anything more, and then just return the result, total value. What's the time complexity of that? Well, sorting, if we're using quicksort or selection sort, not selection sort, other typical sorting algorithm that involve comparison is of n log n. And then you have to go through the list once, so it's O(n), where n is length of items. So the total complexity is n log n. Okay, so let's test it. So test the function, you take the item, take the constraint, and take the key function, right? So the greedy will return the list of items taken and the total value of it. And you can print it out. All right. And then you can change this testing by different key functions. You can use greedy by value, calories, so get value, or you can use a inverse of the cost of that item. This is a Lambda function. A Lambda function we'll talk about later in the later slides, but basically it's an anonymous function with a function with no names, right? Or one-time use function. And then you can also test by the density, which is defined as value to cost pair ratio. And you can use that 800 to test with. So what is lambda function? A lambda function is all synonym is anonymous functions. So the syntax is like this: lambda is keywords in Python, and with the collection of parameters like the function parameters, colon with the expression, which is the function body. So this basically a function with no name, right? Lambda is the keywords. It returns the function of an argument. Okay. You can use lambda function to write complicated lambda functions expressions, but it's frowned upon. Don't do that. Keep that simple. One-liner is the best. Use the normal definition of function instead. Okay. So we can test this with these names, values, and calories, build a menu, and test greedies. Okay. Okay, let me actually try this in code, right? So first of all, let's define a class of food. Okay. In a function, right? We have number of items, value, and weight. Okay. So again, we have name, value, and calories. Okay. So that's that. And bunch of getters. Not gonna. So just all right. So get values, get cost, get density, and that's the basic format of food. And now we're gonna define, build menus. We have names, we have values, and we have calories. Okay, and so menu, initialize the empty list, and a for loop, of values. Okay, and append names I, values I, and calories 5. All right. If I can fix the spelling. All right. So that's build items. Let's define the maximum value. Wait, sorry. Actually, let's define a greedy algorithm. Greedy algorithm picks items, which is in the manual, and have a max cost and a key function. Compare which one is bigger. All right. Item is a list, maximum cost grid equal to 0, key function map elements item to numbers. Okay, so we're gonna do items copy is the sorted function. Items key is the key function. And reverse go to true because we're gonna do the maximum value first. All right. And then result. So basically, we're gonna just pick one by one, right? Initialize total cost, total value, total cost to 0, 0. Okay. And then for I in range length items copy, and let's test if total cost plus items copy I get values, get cost actually is less than or equal to maximum cost, then we can do it, right? Because it's 0, 1 knapsack. So we can append this items copy to the result, and because it's already sorted, add this cost dot cost and total value items copy I get value. Okay, and then finally I'm going to return the tuple of result and total value. Okay, so this is greedy algorithm. Let's test it. Let's test it, test items, constraint, and key function. Okay, so how to test it? Taken value is basically what items were taken, what's the value of them. And that depends the items, the constraint, and key functions. Okay, and we're going to print total value of items taken equal to value, and then in a list we're going to print item. Okay, that's test greedy, and then we're going to define a test greedies with food and maximum units, so different units. Okay, and I'm just gonna give you different, let's test different by value, by unit, by the inverse of cost, and by the density, right? So these three strategies. And then we're going to test this here. If name equal to name. And we're going to do this here. So we have this name's values food, and we can test 800 calories, right? And run it. Okay, so you can see the result. Total value item taken is 285 for 800. If we are using the maximum value, we get this set of using the calories to use the value, right? And we get burger, pizza, and beer. If we use inverse of the cost, we get apple, wine, cola, beer, and donut, right? They are all within 800 calories, but using different values, right? 3, 8, or 18. And then if we use a density like the value to cost ratio, that's the pick. Wine, beer, cola, apple, and pizza. 403 calories. Okay, so this is basically a greedy algorithm. Why you have a different answers? If you choose different key function, because in a this is like two-dimensional functions that you have peaks and valleys, right? But if you are searching near the local area, this area, you have a local minimum, but they may not be a global minimum or maximum. So unless you do the, power set, aka exhaustive search all the search space, you may not be hitting optimum solutions. You don't always yield a global optimum solution. It may be a local optimum. So is greedy density is always a winner? Not necessarily, right? Let's try 1,000. Let's try 1,000 calories and then run again. I'm curious what's going on here. Okay, so in this case, the density is not always a winner. The total value taken is the value. If you sort by value, this is the winner, right? So density is not always a winner. So that means greedy is not always what? So the pros and cons of greedy algorithm, you can see it's very easy to implement. In our case, all we did is to sort some value and just take the best value by your definition of best, right? And it's efficient to compute because only go to n log n does not always yield the best solution. Like you see, the calories varies, depends on how you define the best solution, best function. And you don't even know how good the approximation is because you don't know the answer, the definite answer, right? Unless you exhausted all combinations, then you know the definite answer, but it's computationally expensive. How to find the optimal solutions, like always optimum. Sometimes greedy is giving you the optimal solution, sometimes don't. But greedy is something to consider if you are out of ideas. This is a nice try. The brute force algorithm will always generate a correct answer because it enumerates all the possible combination of items. It removes all combinations whose total units exceed allowed weight from the remaining combinations to anyone whose value is largest. So the question is how to search those large search space. So we're going to do something called search tree implementation, right? So the tree is built top down, starting at a root with the top is an inverted tree. As you already know in our data structure part of the course. And so every time, you start with the root of tree where you haven't selected anything yet, and then you are on to select the first item. And that may not be the optimal solution, so you have a branching, right? So there is a list of considered items candidate, right? If there's a room for that item in the knapsack, node is constructed that reflects the consequence of choosing to take that item. We draw that as a left child, right? And then we explore the consequence of not taking the item, that's the right child. So it's a decision tree. We also call it decision tree. You have pick or not to pick, to be or not to be, okay? And then recursively, you got to non-leaf children. Finally, choose a node with the highest value meets constraint. So let's look at the picture. So here you have knapsack, initially empty. That's a root of tree. And you have to be chosen 3 items, a beer, a pizza, and a hamburgers. So left, always remember, left is the first depth first enumeration, right? So if you take a beer, then you go to left, the beer is in the knapsack, and then you have 2 items left. Or if you don't take the beer, then you only have 2 items left. The bag is still empty, okay? So next time, you just rinse and repeat. At this non-leaf node, non-root node, you do the same selection. Now we are picking pizza. If we pick it, it's left tree, a left node, and you have hamburgers left. If you don't pick pizza, then you only have hamburger left with beer in the bag. And then in the next level, you can either pick hamburger or not pick hamburger. At the leaf node, you can see there is a 1, 2, 3, 4, 5, 6, 7, 8 different combination, which is 2 to the power 3. and you can calculate the value and calorie for each and pick the best one. In this case, the best value is this combination, a beer and a hamburger. 140 with calorie 508, still within the limit. Okay, so take a look at this. This is a called search tree or binary search tree, and this is appropriate for enumeration of power set, right? All right, how to implement that in code? Okay. So complexity, we already talked about it. Each decision tree you have a choice of pick or not to pick. So it's a 2 to the power of I. I is a number of levels. And you can do a prompt of the tree. If any of the combo already exceed the constraint, then you don't need to explore it anymore further, right? But that doesn't change the overall complexity of this approach. It's still 2 to the power of n. So does it mean that brute force is never useful? Let's try it. All right. So let's try a brute force way. So let's try. I'm still going here, but now this time I'm gonna try a brute force. Okay. Let's see. Let's define a different algorithm, brute force. So we call it maximum value, okay? And we have two parameters to consider. That's a list of items to be considered and available. Avail is basically so to consider a list of items, avail is the weight returns a tuple of the total weight of solution to the 0-1 knapsack problem and items that solution. So let's see. If to consider, which is an empty set, right? Or available calories is 0. So you don't have any available calorie to consume, then the result is basically 0 and an empty tuple. So you return a tuple of the total weight. You don't pick anything, so weight is 0, and an item, a tuple of total weight solution, and item that solution. All right, so you don't have any items. Otherwise, we look at the first item in the consider list, right? If the cost of that item, so we're talking about left tree now, right? If the cost of that item is greater than available calories, then we're gonna not to pick that item, explore. So next time we explore the right tree, right decision tree only. So for the right decision tree, right. So we call this recursive function again with, because I don't consider the zeros item, I'm just consider the rest of the list, right? And then available is doesn't matter. It's still the same. Now, the third condition is if the cost is within availability. If then I'm going to pick the next item is this left tree, right? We pick this, and then we explore the left tree, right? We call left tree, which is, so with the value, with the picked value, we take this, then we call the max value with the rest of the list, because I already picked one. So we're gonna just do next one. And remember, we're gonna subtract its cost from it, because every time you take something, you're gonna pay, right? All right, so this is for the left tree. And then remember, we still have a right tree to explore. Wait a second. Oh, okay, yeah. With value also, we also need to add on the current item, right? Because we picked it, so we have to add this to the value. And now we're gonna explore the right tree, right subtree, okay? Right subtree. So right subtree, basically, we don't pick it. Result value, result to take. So we don't take it. We don't take it, then we still consider the rest of the list. However available, it doesn't matter. Doesn't change, right? Doesn't change. And then, so we explore both left and right. Okay. All right. And then we chose a better branch. Which is better? Well, it depends on the value, right? After that, if you pick it, the value is greater than result, then you pick it, right? Is equal to with value and with to take plus next item, the tuple, right? Else, we're gonna pick, we don't pick it. So we either pick the left tree or right tree every time we make a decision. And finally, return the result, okay? All right, so this is basically the brute force algorithm, okay? So take a look at this. Let me test this maximum value result, right? To test it, we just put it here. So basically, we put the food's maximum units, and then we need to build the items to test it. So so to test it, we need some kind of like manuals. We can quickly build manuals like that. Okay. So if to build a large menu, we can do this, right? Basically, we use random. we just import random module. And then we can quickly select between maximum value, maximum cost, a list of large menus. And to test it, we could do something like this. After test greedy, we can do this. So we can build large menu, and we can call test maximum value with items and 800 calories. And that's it. And let's see if we can run it. All right, so it runs. So use search tree, we can see total values 163, 80, and 627. Basically, it's searching through all possibilities, right? But again, you can see that this is taking a lot of time, right? Because it's a very large data set. It's really take a lot of non-time because it's brute force and 2 to the power of n. So next lecture, we're going to talk about so basically this is what we already discussed, right? And if you only have 8 different things, we can quickly test it. But if you have a large sample, it's gonna take a really long time, right? See, it's still searching. It's really so. Next lecture, we can talk about another method to accelerate this, optimize the search space. We call dynamic programming, which will reduce number of calls, right? If we only limited items to eight items, right? Then run it. Then you can see this is really quick. 403 is optimal answer. Yeah, from the exhaust search. So if it's a large manual, we're going to talk about in the next lecture, okay? Which is called dynamic programming. All right, so that's all for this segment. See you next class. Bye.